In this video, we will be learning to balance redox reactions. Redox reactions, remember, are oxidation, reduction reactions. Balance the following oxidation-reduction reaction. CO3 plus aqueous plus nickel solid forms CO2 plus aqueous and nickel 2 aqueous. So here I now have an example of an ionic system. So this is basically a net ionic reaction, a net ionic equation. And these are what we can balance relatively easily because it turns out that all of these obey either rule 1 or rule 2 in our solubility rule table. This first one obeys rule 2. It's an ion, it's a monatomic ion, so its oxidation state is its charge plus 3. Nickel solid obeys rule 1. It's an element in its elemental form, or it's an atom in its elemental form, oxidation state 0. Third one, CO2 plus, the monatomic ion, its oxidation state is its charge plus 2. Nickel 2 plus, again, same case, oxidation state is its charge plus 2. So now I can see what's changing. Nickel's going from 0 to plus 2. Cobalt going from plus 3 to plus 2. So what's happening? Okay, nickel, 0 to plus 2. That is gaining oxidation state. It's losing electrons. It is, therefore, oxidation. Cobalt, plus 3 to plus 2. It's lowering its oxidation state. It's gaining electrons. Reduction. Again, pull apart my oxidation and reduction steps. So oxidation first. I have nickel solid forming nickel 2 plus aqueous. Give yourself some room. Reduction. I have cobalt 3 solution forming cobalt 2 solution. So there I go. Okay, now I can start balancing. First, remember, balance the non-hydrogen and oxygen elements, and they already are. I've got one nickel on each side of the oxidation half reaction. I've got one cobalt on each side of the reduction half reaction. Next, balance the electrons using the oxidation state changes we see in our assignments. So nickel going from 0 to plus 2, it's losing 2 electrons. There's only one of them, so in total I'm losing 2 electrons. Okay, cobalt, plus 3, plus 2, gaining 1 electron. So 1 electron is being gained. Okay. Balance the oxygen, there is none, don't have to worry about it. Balance hydrogen, there are none, don't have to worry about it. Now I've got to balance between these two half reactions the number of electrons. The first one's making 2, the second one's using 1, so I've got to multiply the reduction half reaction by 2. So the electrons are the same. So 2 electrons plus CO3 plus aqueous forms, well, that's 2 CO3 plus aqueous and 2 CO2 plus aqueous. It's a bad capital C. Okay. Now I can add these things together, canceling out what appears on both sides. So it cancels. 2 electrons cancel. I have 2 electrons on each side. They cancel. And what I have left then is my balanced reaction. So Ni solid plus 2 CO3 plus aqueous forms Ni 2 plus aqueous plus 2 CO2 plus aqueous. And there then is my balanced redox reaction for this reaction. Example. One looks considerably more complicated, but in reality we can approach it in much the same way we have before. Okay, so assigning oxidation states as we have. Monatomic ion, rule 2 applies, plus 1. Monatomic ion, rule 2 applies, that's plus 2. This one's plus 2 for rule 2. This one's plus 3 for rule 2. All right. Down here, this is covalent now. That oxygen minus 2 because of rule 3. This hydrogen plus 1 because of rule 4. This oxygen minus 2 for rule 3. Manganese I don't know, but I can figure it out now because of my summation rules. X plus 4 times minus 2 equals a charge on the ion minus 1. So X minus 8 is minus 1. X is plus 7. This is a plus 7 manganese species. Okay, so now that I have that, now I can turn and I can identify what's changing. Well, manganese is changing. Plus 7 to plus 2. Iron is changing. Plus 2 to plus 3. And nothing else is changing. Oxygen, right? Oxygen minus 2, minus 2. Hydrogen plus 1, plus 1. Nothing else is changing. Those are the only two things that are changing. Manganese, plus 7 to plus 2. That's dropping. That's gaining electrons. That's reduction. Iron, plus 2 to plus 3. That's increasing oxidation state. That's oxidizing. And now I pull apart my two half reactions. Oxidation, Fe2 plus aqueous, forming Fe3 plus aqueous. Reduction, MnO4 minus aqueous, forming Mn2 plus aqueous. Okay. Now, balance out the non-hydrogen and oxygen elements, and they are 1 iron, 1 iron, 1 manganese, 1 manganese. They're already balanced. We're good. Now we got to put in our electrons. So that's the next part, electrons. Now, what do I have according to electrons? Iron. First one, iron. Plus 2 to plus 3. I have one atom doing that. One atom is losing one electron. So plus 1 electron here. Now manganese. Plus 7, plus 2. So I'm gaining 5 electrons, and one atom's doing it. So I'm gaining a total of 5 electrons. There I go. Now, next step. Next step is to balance out oxygen. No oxygens in the oxidation reaction, but I have one set here in the reduction reaction. I've got 4 oxygens on the left. I need 4 oxygens on the right, so I'm going to put in 4 waters on the right to make 4 oxygens on the left, 4 oxygens on the right. Now hydrogen. I have no hydrogen atoms in the oxidation half reaction, but I have 8 hydrogens in the reduction half reaction. So I need 8 hydrogens now on the left to cancel that. So I put those in. 8H plus, didn't leave myself enough room, it turned out. I can get close, there you go. 8H plus is now on the left to balance out that. Now I look through and I identify how many electrons are being transferred. The first reaction is making 1, the second reaction is using 5, so I've got to multiply the first reaction by 5 so that they're making and using the same number of electrons. So that first reaction becomes 5 Fe2 plus aqueous forms 5 Fe3 plus aqueous and 5 electrons. Okay, and now I go through and I'm going to add these things together. And I cancel out what appears on both sides. And what appears on both sides is 5 electrons. Nothing else appears on both sides, so that's the only thing I can cancel. And what I'm left with then is my balanced reaction. 5 Fe2 plus aqueous plus 8 H plus aqueous plus MnO4 minus aqueous forms 5 Fe3 plus aqueous plus 4 H2O liquid. This is, oh yeah, plus 1 Mn2 plus aqueous. And there then is the balanced redox reaction for this example. Balance the following oxidation-reduction reaction. Zinc solid plus sulfuric acid makes zinc sulfate and hydrogen gas. We always start these pretty much the same way. We go through and we figure out and assign oxidation states. So this first zinc, rule 1 applies. To neutral atom in its elemental form, oxidation state 0. And if I want to skip ahead a little bit, so is the hydrogen down here. It's an atom in its elemental form, also oxidation state 0. Now, this hydrogen in the sulfuric acid is actually H+. It's a monatomic ion, which means rule 2 applies to it. It's +1. This zinc in zinc sulfate also is a monatomic, because this is really Zn2+ with SO4 2-. This is an ionic compound. So what you really have there is Zn2+ with SO4 2-. So that Zn, I now know, has a +2 oxidation state because of rule 2. So I'm really limited down to just the SO4 parts. Okay, so for SO4, I know the oxygen, all right, based on rule 3 is -2. So really now I'm all the way down to just having to figure out the sulfurs. So over here, 1 sulfur, X. I've got 4 oxygens, 4 times -2. Now, what's the total charge? This is sulfate, and sulfate's total charge is -2. So I have X minus 8 equals -2. X is +6. So this sulfur is a +6 ion. If I did the math, it turns out 1 sulfur X plus 4 times -2 equals -2. It's sulfate again. Notice the math is identical. So this also has a +6 oxidation state on sulfur. And so that's all good. Okay. So that being, now we've assigned all of our oxidation states, and now we can figure out what's changing. Well, it turns out sulfur is not changing, but hydrogen is. Hydrogen, as I can see, is going from +1 to 0. Zinc is going from 0 to +2. And if I assign them based on my rules, the zinc, that's oxidation. 0 to +2 is oxidation. +1 to 0 is reduction. So I've assigned now my oxidation and my reduction. Now, one thing I'm going to very quickly do to make my life so much simpler is I'm going to give up the ions. Because the sulfate, if I look on the reactant side here, I have H+ and SO4 2- as sulfuric acid. That's what I have sitting there. Well, it turns out the sulfate is not changing. I can tell that because the S has 6+ on the left, it has 6+ on the right, the oxygen has 2- on the left, 2- on the right. The sulfate itself is not changing. The only thing that's changing is the H+ and the Zn2+. So that's all I'm going to carry through now. So I'm going to start with my oxidation. So you'll see how I do this. I'm starting out with Zn solid, and what's it becoming? It's becoming Zn2+ aqueous. I'm going to put the sulfate back in at the very end, you'll see. And now my reduction. I have H+ becoming H2 gas. Okay, so I'm good so far. Now balance all of those zinc and zinc, those balance, that's good. I actually need to put a 2 here in front of the H+ because I need 2 hydrogens to get this so I can get my electron count, right? So, zinc. I have 1 zinc atom going from 0 to +2. It's losing 2 electrons. So +2 electrons. Hydrogen. I got 2 atoms doing it. +1 to 0. Each one's gaining 1. So in total they're gaining 2. So gaining 2 electrons. Balance oxygen. Don't have any. Balance hydrogen. It already is. And now balance the electrons between them, and it already is. So now I cancel out what appears on both sides. 2 electrons, 2 electrons. What do I have left? I have left Zn solid plus 2H plus aqueous, Zn2 plus aqueous, H2 gas. I'm going to put back my sulfates back where they go. So Zn solid plus H2SO4 aqueous plus Zn SO4 aqueous plus H2 gas. Done. This is now balanced. So you saw at the very end, I remembered what I took the sulfates off of, so I put it back on them at the end. And because this is H2SO4, that's where the two H's went to. They both are sitting here now, because this is actually two H pluses with one sulfate. Balance the following oxidation-reduction reaction. C2H6 gas plus O2 gas makes CO2 gas and H2O gas. So, how do I do this? Well, the first step in doing this is to assign an oxidation state to each of the elements in this reaction. And I have in the lower right corner of the screen the rules for oxidation state assignment. The oxidation state of any atom in its elemental form is 0, and in this case that applies to the oxygen. So we know that one is 0. Alright, the oxidation state of a monatomic ion is the charge of the ion. Well, we have no ionic compounds, so that rule doesn't apply in this case. In covalent compounds, oxygen gets a -2 oxidation state, except in peroxides, where it has -1. Now, peroxides are things like hydrogen peroxide, H2O2. These are very rare and typically don't show up a lot in general chemistry. So, most oxygens you'll see in these reactions are a -2. For instance, this oxygen is -2. This oxygen is -2. Rule 4, hydrogen is +1 in covalent compounds. Well, here I have a hydrogen, that's +1. Alright, and then fluorine, rule 5, -1 in compounds. I don't see any fluorine. And then the last two rules are basically the summation rule, which says that the sum of the oxidation states of all the elements in a compound must equal the charge on that compound. And this will allow me to solve now for the carbons. So for instance, the first one, I have two carbons. I don't know their oxidation state, so call it 2x. So 2 times the oxidation state of carbon plus 6 times the oxidation state of hydrogen, 6 times +1, must equal the charge on this species, which is 0 because this one's neutral. So I have 2x plus 6 equals 0. 2x is -6. X is -3, which tells me each of these carbons has an oxidation state of -3. Similarly, for the carbon and carbon dioxide, I do the same thing. I have one of them, I don't know the oxidation state, call it X. I have two, so +2 oxygens, each with a oxidation state of -2, and the overall charge is 0. So X plus 2 times -2 is 0. X minus 4 is 0. X is +4. The oxidation state of that carbon is +4. So now I've assigned, oh, and I forgot to label, but I know it already. The hydrogen on the water is +1 based upon rule number 4. Sorry, I forgot that one, or missed it. Okay, so now that that's done, let's give us some room here. So let's erase this algebra here at the bottom. Now that we have some room, let's figure out what's going on in terms of reaction. We look for species that are changing their oxidation state. For instance, oxygen is. It's going from 0 to -2. From 0 to -2. Alright, so is carbon. Carbon is going from -3 to +4. Alright, so carbon is doing the same thing. It's also going in the same direction. So, now we can identify which of these steps is what kind of reaction. Is it oxidation? Is it reduction? All right, so carbon going from -3 to +4, it's increasing its oxidation state, which means it's losing electrons. And to do that, we call that oxidation. So this is oxidation. Oxygen is going from 0 to -2. It's reducing its charge. It's reducing its oxidation state. This is reduction. So now I've identified my two half reactions. Pull apart my half reactions. First, oxidation. Oxidation. What do I have? I have C2H6 gas going to CO2 gas. All right, so that's my oxidation step. Now for my reduction step. Put that below it. Give yourself some room here. I have O2 gas. I have it going to, well, what is it going to? It's going to CO2, but I don't want to include that because it's already included. It's also going to H2O, but I actually don't want to include that either yet because it turns out, well, I guess I could. Let's try and let's actually add it and see what happens. H2O. And there we go. Okay, so let's see what happens if I do it that way. All right, it should work, but it just may be a little bit weird for a minute. So the first thing I do is I balance all of my elements that are not carbon and hydrogen. 2 carbons, 1 carbon on the left in this oxidation, you have 2 there. No other non-hydrogen carbon. Now in the second case, I only have hydrogen carbon, or hydrogen and oxygen. So I need to balance the oxygen. And I need to do that for a reason. I'll tell you what that is in the next step. So I'm going to put a 2 here to balance out the oxygen. Okay. Now, the next step is to put in the electrons that are moving. So in the first reaction, I have each carbon in the oxidation, -3 to +4. It's losing, each carbon atom is losing 7 electrons. So in total, if I have 2 atoms doing it, 2 atoms of carbon doing it, as I do, each one's losing 7, I'm in total losing 14 electrons. In the second reaction, I have oxygen. I have oxygen going from 0 to -2. All right, each oxygen, I have 2 of them, so each one's doing it. I have 2 of them doing it together, so I'm gaining a total of 4 electrons. Plus 4 electrons. Okay. So now I go through, and in my next step, I balance out, in the first case, oxygen and hydrogen. So oxygen I balance with water. I have 4 oxygens on the right, none on the left, so I need 4 waters on the left. All right. In the second one, I have 2 oxygens on the left, 2 oxygen on the right. That's already balanced for oxygen. And now hydrogen. In the first one, I have 8 hydrogens in the first, 6 in the second, that's 14. I need 14 hydrogens on the right to balance that. I put that in the case of 14H+. Second case, I have no hydrogens on the left, 4 hydrogens on the right. I need 4 hydrogens on the left to balance that. So there I see it. And now I have an interesting case of I've got to be able now to balance the number of electrons between these two different systems, between these two half reactions. All right, one's making 14 electrons, the other one's using 4. They've got to be making and using the same amount. To do that, I can find the least common multiple of 14 and 4. So I multiply the first reaction by 2, multiply the second reaction by 7. To get 28, which is the first multiple of each. All right. So, doing all that, multiplying the first reaction, everything by 2, I get 8 H2O plus 2 C2H6 gas forms 4 CO2 gas plus 28 electrons plus 28 H+. Second reaction, multiplying by 7, 28 H plus 28 electrons plus 7 O2 gases plus goes to form 14 H2Os. And now I'm going to take these two reactions and I'm going to add them together, but I'm going to cancel out what appears on opposite sides first. So I have 8 H2Os on the left, I have 14 H2Os on the right, so 8 of them cancel. And that 8 turns this 14 into a 6. So I have 6 H2Os now on the right. Continuing on, 28 electrons on the right and left. So those all cancel. That's good. That's what I need to have happen. 28 H pluses on the right and left. Those cancel out. And what I'm left with is then my balanced reaction. 2 C2 H6 gas plus 7 O2 gas forms 4 CO2 gas plus 6 H2O gas. And that then is my balanced oxidation-reduction reaction. So, in retrospect, having added the H2O in this particular point here before I actually did anything else was okay because I needed to know that 2 oxygens became 2 oxygens so that I get the electrons to work out. All right, which is rather important. So normally we don't add water that early, but in that case we did because there would have been nothing else there.